Hello, everybody. Welcome back. We're going to continue with section 6.4, doing definite integrals. We are in number 1, part E, and we are slowly going up to more and more challenging integrals. So again, a definite integral is where after you finish your integration, you're going to evaluate from the upper bound to the lower bound. But before we can start doing that and plugging in numbers, we have to deal with the integral at hand. We have to integrate just like we would out of section 6.1 and 6.2. Now, we have to look at the function little f that's next to the integration sign. This is the function that we want to integrate to find the big F function, the integral. In this case, because I have something in parentheses to a power here, and I have this other bit of variable x sitting outside of it, I suspect that I will have to do a u-substitution here. So let's do a little bit of cleaning up. And first, I'm going to take this -4 and I'm going to bring it outside of the integral, kind of get it out of my way a little bit. That leaves me with this x sitting in there, but I'm going to move it to the end to sit next to the dx. So all I'm doing right now is rearranging my integral. There we go. Now I see here that I have something in parentheses to a power. Now this looks very similar to things that we did out of section 6.2. So because I have something in parentheses to a power that I want to integrate, I will have to do a u substitution here. So just like we did in section 6.2, you should choose your u to be the function that is in the parentheses, that is raised to the power. So in this case, u should be 3x squared minus 8. And as part of relabeling everything, if this is the function u, so that this becomes u cubed, you have to relabel what x dx is as well in terms of u. So for that step, you have to take the derivative of u over here off to the side to try to replace this x dx term. Now du, the derivative of u is du dx, which we take the derivative of this. The derivative of 3x squared is 6x. The derivative of minus 8 is 0. So we get here. If we multiply both sides by this dx term, you get that du is equal to 6x dx. I'm trying to relabel this integral in terms of this stuff over here. If this is indeed u, so that that becomes u cubed, what is x dx? I'm trying to find a replacement for x dx. Do we see a combination of x and a dx anywhere? I do see an x dx right here. But what is x dx if I treat it as a variable and simplify? Well, if you divide both sides by 6 here, you have 1/6 du is my x dx term. So you look to try to find, well, this is the piece that I still have to remove and replace. Where is that? What can replace x dx? Well, here is x dx. To find the replacement for it, you solve for x dx. In this case, I divided both sides by 6. So what you find is x dx should be replaced with this part, 1/6 du. So that this integral becomes -4 integral -1 to 2 u cubed times 1/6 du. Now, all of my variables are u's instead of x's, which was the point. If we take this 1/6 now and move it out to the front, that becomes -4 times 1/6, which is -4/6, times the integral from -1 to 2 of u cubed du. Now, this looks like something I know how to handle. This is u to the third power, similar to x to the third power. So this is a simple power rule. Let's apply the power rule to u. Remember, the power rule is 1 over r plus 1 times x to the r plus 1, except this time I'm dealing with u instead of x's. So my current power is 3. This -4/6, let's reduce that fraction. That is -2/3. And I'm going to use the power rule on u cubed now. The power rule is 1 over 4 u to the 4th, because r is 3, 1 over 3 plus 1 u to the 3 plus 1. But instead of doing a plus c here and calling it done, we now have to integrate this from -1 to 2. But before you start plugging in 2's and 1's, we have to make a little note over here. You have to put u back into your result before you can start plugging numbers in. U is not, in fact, our original variable. This -1 and this -2 is meant to be plugged in for x, not u. So make sure that you don't forget that step. You integrate, you use your integral rule. Now this is the antiderivative. Once you have your antiderivative, put u back in. So I have -2/3 times 1/4 here. -2/3 times 1/4. U, which is 3x squared minus 8 to the 4th power, that will be evaluated from -1 to 2. -2/3 times 1/4 is -2/12 when you multiply those together, which reduces down to -1/6. So you have -1/6 times 3x squared minus 8 to the 4th power. That's going to be evaluated from -1 to 2. Now, this is where I have to evaluate the definite integral. I have to plug in the upper number, the upper bound, and then plug in the lower bound and subtract those values. Upper value, plug that in, subtract what you get when you plug in the lower value. So first, I want to plug in 2 into all of this, and then plug in -1 into all of that. I'm going to subtract those. So let's do the upper bound first. Let's plug in the 2. -1/6, 3 times 2 squared, which is 4, minus 8 to the 4th power, minus what you get when you plug in the lower number, -1. -1/6, 3 times -1 squared, which is 1, minus 8 to the 4th. Now we get our calculator out, and we start punching out values. This is 12 minus 8. 12 minus 8 is 4. So this is -1/6 times 4 to the 4. Minus minus, minus minus becomes plus. 1/6 times 3 minus 8, which is -5 to the 4. -1/6 times 4 to the 4th power plus 1/6 -5 to the 4th power. 61.5. Now I'm going to double check this real quick. -1/6 times 4 to the 4th. That's this term. -42.66667 plus, let's do this one at a time, -5 to the 4th, which is here, divided by 6, 104. So yeah, that looks like it's good. -42.66 plus 104.16667. We get that 61 and some change. So this looks good. It's never hurts to go back and check your calculator. It's easy to just press the wrong button and get the wrong result. So we get this as our value for the definite integral. Remember, definite integrals, you should have a number as a result instead of a function. So this is what we have for this integral. 61.5. And as a reminder, if I wanted to give this meaning, this is the area that is underneath this curve when you graph it, between this curve and the x-axis, in between x is equal to -1 and x is equal to 2. So now let's do part F. Getting lots of practice with definite integrals today. Find the antiderivative of 1 over 4x plus 1 to be evaluated from a to 4. Now, if you notice, this bound is a letter instead of a number. That is the letter A. But we're going to treat that as a number and pretend it's a number and plug it in at the end like we always would. So A is considered to be some constant. So first, we have to figure out how to handle this. When I have 1 over 4x plus 1, you might recall from section 6.2 that whenever you had a function in the denominator like this to a power of a -1, another way you can think about this, that is, you can raise that whole term into the numerator, making it 4x plus 1 to the -1. But when you integrate x, just plain old x, remember the integral of 1 over x, or x to the -1 is ln. This looks very similar to an x to the -1 power, except it's not x to the -1 power, it's something in parentheses to the -1 power. And as soon as you see something in parentheses to any power, you should think u-substitution, which comes from section 6.2. But in this case, the u-substitution I'll have, since this is a -1 power on it, I will have an ln after I integrate instead of a power rule. But let's take care of this one step at a time. If this is something in parentheses to a power, you should choose your u to be the thing in parentheses, the 4x plus 1. That's your substitution. So now this whole thing will become u to the -1 instead of 4x plus 1 to the -1. The only problem is that I still have to trade out this dx term. Every single piece of my integral must be traded out. So to figure out what my dx is supposed to be, I come over here and I take the derivative of u. Du dx is derivative of 4x is 4, derivative of 1 is 0. Solve for du by multiplying both sides of the fraction by dx. Du is 4 dx. I'm looking for a dx somewhere over here. And then I go, oh, I have a dx right there. If I want to trade this piece out, I've got to solve for what this dx equals. So I'm going to divide both sides of this equation by 4. dx is du divided by 4, or that is 1/4 times du. So now I'm going to trade out this dx term with that 1/4 du that I found. So now my integral becomes integral a to 4 u to the -1 times 1/4 du. To finish my integral, now that this 1/4 du is in here, you can move any constants to the front. So this becomes 1/4 times the integral a to 4 u to the -1 du. All of this has been set up. I haven't actually integrated yet, but now that I've traded out all of my functions for u's, now this is easily identifiable, and all the constants are in place. I have u to the -1. The integral of x to the -1 is ln x. The antiderivative of u to the -1 is ln of u. So now I'm actually going to do the integration. The antiderivative of u to the -1 is ln of u. And this will be evaluated from a to 4, and this 1/4 goes out in front of the ln u term. Now, I'm not quite ready to start plugging in 4 and a. 4 and a are supposed to be plugged in for x. So before you can start plugging in numbers here, you should put u back by plugging it back in. So what was u before we integrated? Well, we said u is 4x plus 1. So put it back. We have 1/4 ln of 4x plus 1, and that's to be evaluated from a to 4. Now I'm ready to start plugging in numbers. Plug in the upper bound first, upper minus lower. So plug in x equal 4 into this whole thing here. Get 1/4 ln 4 times 4 plus 1. 4 times 4 is 16, plus 1 is 17. upper bound plugged in, minus what you get when you plug in the lower bound. Now my lower number is a, so it's not really a number, but you still want to pretend and plug it in for x as if it was. So this becomes 1/4 ln 4a plus 1. So my result is 1/4 ln of 17 minus 1/4 ln 4a plus 1. Since I don't actually have a value for what a is, I can't actually solve for this. You could punch out the 1/4 ln of 17 if you liked, but I wouldn't bother with it since ultimately you can't even punch this out anyway. So I would leave this as it is. This is my result. 1/4 ln 17 minus 1/4 ln 4a plus 1. This is ln of 4a plus 1 and ln of 17. And then we're done with this problem. We scooch on over to the next page. Be the last one we do out of this problem. This is the integral from 2 to 6 of 3x over x squared minus 3. When I look at these, I always have to try to decide how it is I can integrate. First of all, I have 3x in the numerator of a fraction. But this is a fraction where my denominator looks to have the power of 1. There's no power on this down here. So that is to say, if I manipulate this a little bit, I can bring up the x squared minus 3 term into the top. So this becomes the integral from 2 to 6 of x squared minus 3 to the negative 1 power times that 3x dx. Now I haven't integrated anything yet. All I'm doing is changing the structure of this function so that I can better identify how to deal with it. So the next thing I notice is I have a loose constant here that I can relocate. And I definitely want to do that to get it out of my way. This is 3 times the integral 2 to 6 x squared minus 3 to the negative 1 x dx. The next thing I notice is I have something in parentheses here raised to a power. So generally, if you have some expression in parentheses raised to a power, you should think u-substitution. And I also notice, I'm kind of seeing into the future here a little bit, the power on this is negative 1. So this is going to be similar to the problem I just did. Because I have a negative 1 power on there, after I do the u-sub, I'm going to have to use an ln rule to do the antiderivative. But before we get there, let's actually go through the motions of assigning our u and doing our integral. The u is always the part in parentheses, the x squared minus 3, which has the negative 1 power. So if this is u, that whole thing becomes u to the negative 1. But I still have to trade out my x dx. So I need to figure out what is this piece of the puzzle equal to? What is x dx? So I'm trying to find, where's Waldo? Where is an x dx term? So for that, I try to invent one. I have to come over here, take the derivative of u. The derivative of u is du dx. The derivative of x squared is 2x. The derivative of minus 3 is 0. Multiply both sides by dx so that you get du is equal to 2x dx. And then boom, magically, I have my winning combination of something I'm looking for. I was looking for an x dx. How convenient is that? There's my puzzle piece. But it has a 2 in the front of it, and I want to get it by itself. I want to get the x dx by itself. So divide both sides by 2, and you have the du divided by 2, or that is 1/2 du is x dx. So swap out x dx with the 1/2 du term. This becomes 3 times the integral 2 to 6 u to the negative 1, 1/2 du. I have done my swapping. Let's take this 1/2, now that it's in here, and move it to the front of my integral. That becomes 3 times 1/2, which is 3/2. integral 2 to 6 of u to the negative 1 du. Now I haven't actually integrated yet. What I did was I swapped out the parts of my integral to make it more identifiable. U to the negative 1, I know what the antiderivative of x to the negative 1 is. It's ln of x. The antiderivative of u to the negative 1 is ln of u. So now I'm actually doing the integration. I have to use the ln rule, so this becomes 3/2 times ln of u. And this is going to be evaluated from x going from 2 to 6. So before I can start plugging in numbers, I've got to put u back. So plug, now that you've integrated, the calculus part's done, you've done your job, put u back. Now that that's over, you have 3/2 ln x squared minus 3, ln of x squared minus 3, to be evaluated from 2 to 6. Now finish up your integral by plugging in the upper bound first into all of this, 6 plugged into that, minus what you get when you plug in the 2. Upper bound minus lower bound. So plug in the upper bound, 3/2 ln 6 squared minus 3. That's ln of 6 squared minus 3. So upper bound plugged in first, minus what you get when you plug in the lower bound. Plug in 2. You get 2 squared minus 3. Now the rest of this is definitely a calculus exercise or calculator exercise. So you can get out your calculator here and start punching stuff out. But what this will give you 3/2 ln of 36 minus 3, be ln of 33, minus what you get, we have 3/2 ln of 4 minus 3, which is 1. Now ln of 1 is actually 0, and 0 times 3/2 is 0. So this is going to be 3/2 ln of 33, whatever that equals. So you can plug this into your homework and it will accept that as your answer. But if you want to calculate this as a decimal, 3/2 ln 33. We get 5.244, and it said to round to 2 decimal places. So our answer we would plug in would be 5.24. That's the answer for this integral. All right, let's move on to our next problem, which is problem 2. Now this is where they start to have us do integrals, but they put them in a word problem, assign meaning to them. It says find the total area bounded by the x-axis and the curve 8x squared plus 7x plus 6 on the interval -1 to 2. Enter your answer in exact form or as a decimal. So when they say find the total area bounded by the x-axis and the curve, they mean the area. If we're to graph this, let's graph it. We'll see what this looks like. Here's my curve. Let's put it in the calculator so I can see it. This is what it looks like. And let's zoom in a little bit. Can't see it very well. All right. Zoom back out. Well, there it is. And it says we want to know what is the area between -1, x equal -1 is down here, between x equal -1 and 2 that's underneath this curve. So if I were to zoom in and it looked nice, I have my parabolas right here. It looks a lot worse than that. But I have my axes down here. We have x equal -1 to 2. And what we want to do is find the area between the curve and the x-axis and -1 and 2. That would be this area right here. And as it happened, and I mentioned this last time, that's actually what the definite integral means. This value that we keep finding, the definite integral from a to b of f of x, that number we get is actually the area under the curve between the curve and the x-axis and those x values. So basically what they're telling you to do here is do a definite integral. So you are going to integrate your function 8x squared plus 7x plus 6. And it wants you to integrate it from -1 to 2. -1 is your lower bound, 2 is your upper bound. That is the range of x that you want to find the area in between, -1 to 2. So this result, the number you get that we've been calculating, is going to be this area under there. So let's evaluate this. How would I integrate? Well, this is a function to the first power, meaning it doesn't actually have a power on it. I don't have to use a u-substitution here, but I can integrate this term by term. You can integrate 8x cubed using a power rule. You can integrate 7x using a power rule. You can integrate 6 using the constant rule. So let's integrate this term by term, and then when I'm done, I will evaluate upper bound minus lower bound. So the antiderivative of x squared, and I'd have a power rule there. Remember, the power rule is r, 1 over r plus 1, x to the r plus 1. My r is 2, so you will have 8, 1 over r plus 1, x to the r plus 1. And that takes care of the first term. Plus 7. This is x to the first power, so I am going to use a power rule on that. 1 over 1 plus 1, x to the 1 plus 1. And the antiderivative of 6 is 6x. This is all to be evaluated from -1 to 2. So what you're going to do is you're going to plug 2 into all of this, punch that out, and then plug -1 into all that, punch that out, and subtract them. Let's plug in 2 first. You have 8 thirds, 2 cubed, plus 7 halves, 2 squared, plus 6 times 2. That's the upper bound plugged in, minus what you get when you plug in the lower bound, -1. 8 thirds, -1 cubed, plus 7 halves, -1 squared, plus 6 times -1. Upper plugged in minus lower plugged in. All right. Now at this point, you can get out your calculator. Let's see what happens here. Let me simplify this down a little bit more. I have 8 thirds times 2 cubed, which is 8, which becomes 64 thirds, plus 2 squared is 4. 4 times 7 is 28. 28 halves, which is 14, plus 12. So I have 63 thirds plus 14 plus 12, minus what you get here. This becomes -1 cubed is -1, times 8 thirds is -8 thirds, plus 7 halves, because -1 squared is 1, minus 6. Punch this out very carefully. I like to punch out this part first, and then subtract what you get when you punch out that part. But when we do this in our calculator, we get the value is 52.5. So this is the area between this curve and the x-axis between -1 and 2. 52.5 units. All right. Let's do number 3. It says find the average value for f on the interval. Now to do this one, I've got to look at my front page. We have a definition here that we haven't talked about yet. What does it mean to find the average value? We need a term for that. We need a definition. So if I come back to my first and second pages, where all my definitions are, I need this fella, number 5. It says, for a function which is continuous on an interval a to b, remember this is the same a to b that's on your bounds of your indefinite integral, the average value is 1 over b minus a times the integral from a to b of f of x dx. So the only difference between the definite integral and an average value an average value has 1 over b minus a in front of it. The rest of it's the same. You have a to b of f of x dx, but if you have 1 over b minus a on the front, that little fraction out front, then it becomes an average value. So let's come back over here, steal this formula, and apply it to this problem. The average value of anything is 1 over b minus a, integral from a to b of f of x dx. So this is my function I'm going to be integrating, and they give you an interval, 1 to 4. This is your a to b. 1 is a, and b is 4. So let's plop this all in my formula. So now I have this little fraction out here, 1 over b minus a. 1 over b minus a times the integral a to b of f of x dx. So this becomes 1 over 3 integral from 1 to 4 of 8x cubed plus 6 dx. Now this is, again, does not have a power on the outside. I do not have to do a u-substitution. I can integrate this term and this term separately. This will involve a power rule. This is the integral of 6. Let's go ahead and do that. You have 1/3 times, do a power rule here, r is 4. You have 8 times 1 over r plus 1, x to the r plus 1, plus 6x. The integral of 6 is 6x, and I have this 1/3 that gets multiplied by both of those guys. And this is all to be evaluated from 1 to 4. Let's clean up the inside a little bit before I start plugging in numbers. I have this 1/3 sitting there. 8 times 1/4 is 2. So I have 2x to the 4th plus 6x times 1/3 to be evaluated from 1 to 4. Now I'm ready to plug in numbers. Plug in 4 into all of this and subtract what you get when you plug in 1. So let's work on it. 4 to the 4th plus 6 times 4 minus what you get when you plug in 1 into all that. 1/3 times 2 times 1 to the 4th plus 6 times 1. I have 1/3 times, I'm going to start using my calculator here. 4 to the 4th times 2 is 24 minus 1/3, 2 plus 6. We now get 256 over 3 minus 8/3, which is 176 when you punch it out. This is the average value of this function between the values 1 and 4. The average y value that the function takes on is a height of 176.